Welcome everyone. Welcome to today's lecture. So today I'm going to discuss Laplace and Poisson's equation. So this topic is extremely important for us as we are studying in officers batch. Every year you will see in UPSC Geophysics, there is definitely one question or two questions from this topic which are asked. And the level of question is very straightforward, direct problem, and you just have to know the very basic concepts and you can solve this problem. So this one topic, today's 30-40 minute lecture will give you 3.5 marks for sure in UPSC Geophysics Prelims. And also if I talk about this topic has been directly asked in IIT JAM exam, in JEST examination, in GATE and NET examination. So in all of these examinations, this topic has been there. And we need to know the very basic part of it. So let's begin. Now, in electromagnetism, we have a very basic story. The story says something like this. Electric field is something we need to find, or let's begin. We need to find force. But one way to find force is Coulomb's law, K Q1 Q2 by R square. But it is not very easy to find Coulomb's law or use Coulomb's law every time because it is little difficult to solve Coulomb's law for the complex problems. Okay, then we say, okay, rather than finding force directly, we can find electric field, and force is given by Q into E. So once we know electric field, we can find force. And for electric field, we use Gauss law. And sometimes Gauss law also become difficult to solve because electric field and force are in reality are the vector quantities. And it is always difficult to deal with vector quantities. Then we say, okay, it's good idea that electric field is conservative in nature. So let's find potential. So once we know potential, then we can write our electric field as minus of gradient of V. So then we can find electric field, and that will be much easy because potential is a scalar quantity and it is easy to deal with scalars. So then the question comes, then how will we find the potential? What is a methodology to find the potential? There are multiple ways. One problem you might have seen is image problem. One might you have seen is you can say is the multipole expansion. One might be the potential formulation. But one technique or the one equation which is needed to be solved to find potential is Laplace equation and Poisson equation. So these are the two fundamental equations, and if you solve these equations, you will get potential. So once you know electric potential, you can find electric field, you can find electric force. And why we are so interested in finding electric potential? Because it's a scalar quantity and it is easy to deal with scalars than to deal directly with the vectors. So let's do that. So we will do that and we will solve the two equations. So what is Laplace equation? Laplace equation is basically del square V equals to 0. So del square is basically here a Laplacian. In our vector classes, we have done del square means the gradient of the divergence of gradient. So first you find the gradient of V and then you take the divergence of it. You will get the Laplacian. So del square V equals to 0. And on the other hand, we have a Poisson equation which says del square V equals to minus rho by epsilon. Both of them are the same equations, but it's just we have to understand very carefully. When your space do not have any charges, means you're talking from, let's say you have two charged plates. This plate has a plus Q charge and this plate has a minus Q charge. Between these two plates, there is no charge. So if I'm trying to find the potential between these two plates, then I do not have any charge between these two plates. So I will use Laplace equation where I will say del square V equals to 0. And these two plates will act as a boundary conditions. Okay, within these two boundaries, I do not have any charge, so I will use Laplace equation. And these two are basically my boundaries. Here I have some charge, here I have some potential, here I have some charge, here I have some potential. These are my boundaries, but between my boundaries, there is no charge. So we directly use Laplace equation. But on the other hand, let's say in between, I say that, okay, there is a sphere which has a positive charge plus small q. Okay. Then I cannot use this. Then I have to go for the Poisson's equation. And going for a Poisson equation is all not very easy. Okay. So that is why in our syllabus, we have the Laplace equation. We need to use the Laplace equation, and Laplace equation is very powerful. For most of the cases, you can use Laplace equation, right? So let's try to understand how we can solve Laplace equation. Okay. Now Laplace equation has to be solved in 3 coordinate systems. Number one, we have to solve in Cartesian. In Cartesian also we will study 2 concepts. One is 1 dimension and one is 2 dimensions. And then second of all, we come for the spherical coordinates, and then third will be the cylindrical coordinates. So I will begin with the solution in the Cartesian coordinate. So now my entire purpose is to solve this equation and find out something or find out potential. That's all. That is my entire idea. When do I use Cartesian coordinate? When do I use spherical? And when do I use cylindrical is the most important part. So Cartesian is used whenever you have a planar symmetry. Planar symmetry means your potential is depending upon the values of x, y, and z. Right? So let's say you are on the surface. Surface symmetry or a plane symmetry results in the Cartesian coordinate system. On the other hand, let's say your potential only depends upon the radius from a certain point. So let's say this is your point, and if you go 3 meters here or 3 meters here or 3 meters here, it does not matter. At all these 3 points, potential will be same. So let's say this is my center point. If I go 3 meter here, 3 meter here, or 3 meter here, at all these 3 points, my potential is same. Then it means I do not have a planar symmetry. I have a radial symmetry. I have a spherical symmetry. So I will use spherical coordinate system. On the other hand, let's say I have this line charge, and if I go 3 meter here, 3, 3, 3, 3, 3. Now I am getting is a cylindrical symmetry. So based on the symmetry you have involved in your system, point sources usually have radial symmetry. Line sources usually have a cylindrical symmetry. And more or less any random orientation usually could have or may not or maybe or may not have a Cartesian symmetry. Okay? You can use any coordinate system, but the problem is that you have to choose the most easy one. Okay? If you have a radial symmetry and you're using Cartesian, you will get an answer. But the problem is that you will get an answer with 1,000 times more difficult ways. So we need to choose our coordinate system very carefully. Most of the times the question itself hint you that what you are going to need to use. That's all. You usually never in my question I have to think which coordinate system to use. Always it is always given in the problem itself, and it is clearly given. You can easily detect which coordinate system has to be done here. Okay. So let's first of all understand the Cartesian coordinate, how to solve in Cartesian coordinate. So we are understood that we have a planar symmetry. So we will understand two concepts. One is 1 dimension and one is 2 dimension. So let's first go for 1 dimension. So the very famous problem in 1 dimension, which is if you understand this problem, you understand the entire concept, is that consider the 2 parallel plates. So you have 2 parallel plates. So plate number 1 and plate number 2. They are in XY plane. So you see this is your X and this is your Y. So both of them are in XY plane, parallel to each other, but the planes are XY plane. And they are separated by the distance D. So the distance between these 2 plates is actually D. And this is a Z axis. So this axis is your Z axis. So the perpendicular axis is the Z. Right. Now the potential is only changing with Z. So if you're here, the potential is something else. If you're here, something else. If you're here, something else. So the potential is only changing with one parameter, which is Z. It does not change with X or it does not change with Y. So if you're here or if you're here, if you are here, everywhere the potential is same. Because in this plane, at every point Z is D, and at this plane, every point Z is 0. So wherever you go in this plane, potential will be same. Wherever you go in this plane, potential will be same. But if you're trying to go in Z direction, up and down, then the potential will change. So potential in this case is only depending on one coordinate, which is in our example is Z coordinate. That is why this is 1 dimension. Keep potential only depending upon the one parameter, which is Z. So that has to be understood very clearly. So number one thing we understood is that potential is only depending on the Z. So it's a 1 dimension case. Okay. Now del square V equals to 0. So this is our Laplace equation. And as you can see, there is nothing in between. So that is why we can use Laplace equation. And these two will act as a boundaries. So this is my first boundary, second boundary. Between there, I have no charge. So del square v equals to 0. Now del square v in Cartesian coordinate can be written as curly square v by curly x square plus curly square v by curly y square plus curly square v by curly z square. Now first two terms are meaningless for us because v does not depend upon x, so this is anyway going to be 0. V does not depend upon y, so that is also going to be 0. So only thing that is going to remain is del square v by del z square, because v only depends upon z. So that is why I can write del square v by del z square equals to 0. And the solution to this equation is az plus b. I'm going to give you a very basic hint how to solve this equation, and I think this is any class 12th student can do that. So this is my equation. First step you have to do is integrate. So if you integrate, you get curly v by curly z. Integration of 0 is 0, but you have to add a constant because it's an indefinite integration. So let's add a. Okay. And now what I can do is I can just keep my dv on this side and dz on other side. Right. Then again integrate. So dv integration is v, a is a, integration of dz is z, and then another constant b because it's an indefinite integration. So finally your result come out to be az plus b. And that is the most important result. Most important. If your potential is only depending upon the one parameter and you are in a Cartesian coordinate, then the final potential will be az plus b. Potential is linearly depending upon z or a distance. A and b are some constants which depends upon the boundary conditions. So once you have the boundary conditions, okay, what is the potential at this boundary? What is the potential at this boundary? If you use those boundary conditions, you can find the value of A and B. So that was your entire concept of one dimension. Okay. Now we will see that where exactly we can use this. Okay. So before I go for that, any doubt in this one till this point? So here now we have is a UPSC Geophysics Prelims question, which are very latestly asked in 2024. And let's see within this, whatever we learned in last 5 minutes, can we solve this problem? So again, they say consider the two metal plates. Yes. Each having an area A. Okay. We have two metal plates. Each are having an area A. They are parallel to the XY plane. Okay. So our plates are in XY plane and they are separated by a distance D along Z axis. So don't think that I have taught you the topic from this question. No. What I have done actually is I have picked up the Griffiths book, and that previous derivation was a direct part of a Griffiths book. So they are asking a very, very standard questions. UPSC is especially asking very basic and very standard questions in prelims. They are not going broad with physics. At least in physics part, they are not going to ask you something very off the chart. Clear? Okay. So now if the upper plate is held at a fixed potential V0. So upper plate means the plate which is at distance Z. So if your Z is D, upper plate has Z equals to D, the potential at the upper plate is V0. And the lower plate, which is at Z equals to 0, is grounded. So grounded word means the potential will be 0. You connect it with the ground and ground have a potential 0. So whenever you see the word grounded, the grounded word means the potential is 0. So at Z equals to 0, your potential is 0. So these two are going to be our boundary conditions. So these are my boundary conditions. Now what they're asking is that find the potential distribution along the Z direction. How the potential depends upon Z. So first of all, I will use the standard result that my potential is V equals to AZ plus B. Perfectly fine. If I put Z0, here, so this will be 0 and this. So if I put Z0, my potential is also 0. So this is going to be 0. This is going to be 0. So B will become equals to 0. Right. So if this and this goes to 0, then B is also 0. Hence, my B is coming out to be 0 for this example. Then the second example. What if I put Z equals to D? So if I put Z equals to, if I put Z equals to D here, so this will be AD. B is already 0, so I don't have to take that. And V is equals to V0. So V is equals to V0, A is A, Z is D, and B is anyway going to be 0, so that is all gone. And from there, I can say A is equals to V0 by D. A is equals to V0 by D. And now I will just take my advantage and I will put my values here. So A is equals to V naught by D, and then I have Z, and B is 0. So this is my final result. So the potential is going to be V naught Z by D, which is my option number D. So within 1 minute, you can solve this problem out if you have seen this topic before. So is this question clear to all of you? Yeah. So this was a direct question being asked in 2024. Please let me know, is it clear to all of you? So this problem was asked in actually UPSC Mains 1 2023. So I leave this question for you. You can try this out and you get this notes. Very easy, straight away. The same things we have done before. Okay. So this will remain your homework. I don't need to explain this. You know this. Okay. Now I want to go for 2 dimensions. So now my potential will not only depend upon Z, it will also depend upon something else. So it will now depend upon 2 parameters. So let's see how the question would be there. And again, the question is from the prelims, but the derivation I'm taking is from the Griffiths book. So Griffiths book has a very standard derivation for this exact example they have in the book as well. So they are taking the direct example from the Griffiths book itself. So let's study. And once we do this derivation, all your 2D cases will be covered. So they say now they have a rectangular pipe. So now they don't have a plate, they have a rectangular pipe. So I am showing you the pipe. You can see here, it's a good diagram for a pipe, you can imagine. It is running down or running parallel to the z-axis. So basically this is your z-axis. You can see there. And it is an infinite pipe. So it is going from minus infinity to plus infinity. It has 3 grounded metallic sides. So basically it has 4 sides. If you see top, bottom, left, right. So this pipe has 4 sides total. Out of those 4 sides, 3 is grounded. So which sides are grounded? X equals to 0, y equals to 0, and y equals to a. Now x equals to 0 is this back side. X equals to a is this front side. Y equals to a is the top side. So these 3 are 0. So their potential is 0. So potential is 0 at x equals to 0. Potential is 0 at y equals to 0. And potential is 0 at y equals to b. Y equals to a. Okay, not b, but a. Clear? Does not matter. The symbols does not matter. Okay. So this is what is given to us. So 0 and y equals to a. Sorry. So y equals to 0 is the top side. No. Y equals to 0 is a bottom ground, and y equals to 0 is a is a top. So these two are at a 0 potential, and then also x equals to 0, which is a backhand side, that is also 0. So top, bottom, and back are at 0 potential. And the 4th side, which is at x equals to b, which is the front side, is actually at potential v naught, is at a specific potential v naught. So at x equals to b, the value of potential is v naught. However, all of this does not matter to solve the problem, because they are not in the last step, they're not using the boundary conditions. But anyway, they are giving you this information has been given just to make sure that you use the 2-dimension case. Okay? Because in this you see that boundary conditions are depending on x and y. So depending upon which side you are on, your potential will not only just depend upon z, it is not at all depending on z, it is depending on x and y in this case. And you can even look at the options. Your final answers are in terms of x and y. So your potential is depending on x and y, 2 things. And the boundary conditions are also given in such a way that, so whenever a rectangular pipe comes, whenever the 2 parallel plates are there, you have 1-dimension case. And whenever you have a rectangular pipe kind of situation, then you have a 2-dimension case. Clear? If this would have not been infinite, let's say it was a finite, and then they give you the potential of this side and this side as well, then it will be 3-dimensional case. Okay? In this case, the pipe is infinite. That is why your potential is not depending on z, it is only depending on x and y. But if this pipe would have been finite in length, then it would depend, and then they will give you the potential at this side as well and on this side as well. Then it will go to the 3D case. Okay, perfect. Sir, with this much information, now we are almost ready to solve our problem. Okay. So now what they are asking, so which one of the following can be taken as a suitable trial solution for an overall potential Vxy by solving the corresponding two-dimensional Laplace equation. So UPSC is so considerate. I mean, if this were been in a physics exam, they would have never mentioned two dimension. But UPSC is so considerate because they know that both UPSC geophysics and physics students both are writing this exam. They have even mentioned it that solve it in the two dimension. So which makes our purpose much more easier. So we know now we have to solve the Laplace equation in two dimensions. Okay. So what kind of solution we will get? Out of these four, what kind of solution we will get? That is our question. Okay, let's begin. So in two dimension, our potential is only depending on x and y. So we will say Laplace equation is del square v equals to 0. So curly square v by curly x square plus curly square v by curly y square equals to 0. There is no meaning to take the z term because that is anyway 0. Your potential is not depending upon z. That is why this thing is 0. Gone. Now in physics, we have a very particular, every physicist, if this method fails, they do not have any backup plan. Most of the cases, physicist has one way, and the second way for physicist is actually directly PhD. Either you are solving a PhD problem or you are using this method. Okay? So what is this method? This method is known as variable separation method. This is used in quantum mechanics while solving the wave functions. This is used in electromagnetism while solving the potentials. This is used in wave equations while solving the fluid mechanics and waves. In every branch of the physics, this one method is the most important, which is known as variable separation. Variable separation method assumes one thing, that the solution of x-axis and y-axis are independent. And so your total potential is actually some function which depends upon x multiplied by some function which depends upon y. For example, sin x into cos y. So your solution will look something like this. They are not saying that exactly sin and cos will come. They are saying it will look something like this, in which two functions are being multiplied. One is a function of x and second is a function of y. And they both are they both are independent to each other, and then you can find both of them separately and then you can multiply. That is the assumption of variable separation method. So variable separation method says whenever you're solving the partial differential equations in 1D, 2D, 3D, so this is a partial differential equation, right? In that case, you can use a variable separation technique in which your final solution will be the product of two functions, or if it is a three-dimension case, three functions. In this case, it's a two-dimension, so it is a product of two functions. One function is only a function of x. So one function will be sin x, cos x, log x, ex, whatever. And second function is only a function of y. So second will be cot y, tan y, sin y, e ki power pi, log pi, whatever. But it will be just y. And first will be just x. And you can just multiply them. Okay? So one function we are saying is a capital X. Capital X is only a function of small x. And the second we are giving a symbol as capital Y. Capital Y is a function of y. Now capital X can be sin cos anything. Capital Y can also be sin cos anything. Okay? It can be trigonometry, log, exponential, hyperbolic functions, whatever. That depends upon our problem. So this is our assumed solution, and this is going to be our assumed solution always. So let's put it in our equation. So if I do put it, so first of all, I am differentiating with x. So y does not plays any role. So it is a constant. So I keep it outside. So y remains outside. And then I'm differentiating capital X with small x. Capital X is a sum function. So I'm differentiating that function with my x parameter. Small x is a small x, means it's a coordinate. But capital X is a symbol for some function. It will be a sine or maybe cos x or a tan x. So capital X is not a x. Capital X is a symbol of some function. Okay, good. Next, in the second case, I'm differentiating with y. So my capital X is going to play no role. So that will just keep constant outside. And then I'm differentiating my capital Y, which is some function, with my small y equals to 0. Now what I want to do is that I want to decouple this equation. My equation is coupled because if you see in this x and y both are available. In this also x and y both are available. I do not enjoy that. I want to decouple my equation. So in order to decouple, I will divide entire equation by xy. Right hand side is anyway 0. So if I divide anything on right hand side, it is going to be 0. But on left hand side, a very important thing happens. Because if I divide this by x and y will cancel, and I will be remaining is 1 by x into d square x by dx square plus 1 by y into d square y by dy square equals to 0. So now I have decoupled my equation. So this term now only has x terms and this has only the y terms. And that is very important. So this term changes if I change x, but this term does not change if I change y. This term cannot change if I change y. And this term cannot change if I change x. So it is basically, you are basically adding two boxes, and these two boxes are giving you 0. This box only depends upon x and this box only depends upon y. Okay? If they are adding together and giving you 0, it basically means that both of them are constants. And why I say that both of them are constants? Because, for example, let's say I change x. If I change x, so let's say the equation was satisfied. Equation was satisfied. So now I change x. So if I change x, this value will change. So initially, let's say this thing was 2 and this thing was -2 and you are getting 0. Now I change x. So if I change x, this thing may become 3, but this thing will not change because this thing only depends on y. So this will remain -2. So the equation is no longer satisfied. Equation is no longer satisfied. So if I am changing x and y, and even if one of them changed, then my equation will no longer remain satisfied. So in order to keep my equation satisfied for rest of my life, I have to say that these two should remain constant. If this is 2, this will always be 2. And if this is -2, this will always be -2. So that 2 minus 2 will become 0. Okay? So that is the most important part. Because if I change x, x can only change this thing. It cannot change this thing. So if 2 minus 2 was 0, and if you just change one of them, 2 becomes 3, then equation will not be satisfied. Or let's say you change the y term. This becomes -2 to -3. Now, again, the equation is not satisfied. So by changing x or by changing y, you can only change one term and then other term will not change. That is why this equation will no longer remain satisfied. So that is why both of these things have to remain constant. Means if you change x and y, does not matter. This will remain 2, this will remain -2. All the time equation is satisfied. And that is also one of the concepts we use in the variable separation technique. Our both deep coupled equations are always constant. So this is one constant k. So let's say this term is k. So obviously this is going to be -k. Only then k minus k will be 0. So one side is k, another side is -k. Okay. So then I take this term on other side, or no need actually. Sorry, not this term. This thing on other side. So you get d square x by dx square equals to kx, and in this case I get d square y by dy square into -ky. We have already discussed these two. If you remember, in one of the interview classes I conducted with the officers batch with you all, we understood the difference between these two differential equations. Do you remember that, anyone? We studied that what is the difference if there is a plus sign here and what is the difference if there is a negative sign, right? In one of the case, the solution will be hyperbolic functions, or you can say e की power kx and b की power e की power minus kx and so on. So the solution to this equation is actually x equals to a into e की power kx plus b into e की power minus kx. On the other hand, the solution to this equation will be c into iota ky plus d into e की power minus iota ky. In this side there is no iota, but on this side there are iota, because this is a harmonic solution. Means the solution to this will be sine and cos, and the solution to this will be sine hyperbolic or cos hyperbolic. So if d square x by dx square has no negative sign here, then the solution which comes out is hyperbolic functions. But if there is a negative sign here, then the solution which comes out is a sine and cos. Okay? Or you can say e की power kx and e की power minus kx, or e की power iota ky or e की power minus iota k. Iota ky and d minus iota ky can also be written in terms of sine and cos. You know the de Moivre's theorem, e की power iota theta is cos theta plus iota sine theta. That is what I'm using. Okay. So all of this goes to hell, and what we need to know now is that my x is equals to e की power kx plus b into e की power minus kx, and my y is equals to c sine ky and d cos ky. Okay. Maybe in some solutions they will be writing iota ky or minus iota ky. That will also be equally true, because de Moivre's theorem says that iota ky or iota theta can be written as cos theta sine theta. Okay. So this is my x and this is my y. So the first step that I did is, when potential is a multiplication of two functions x and y, then I said, okay, I decoupled the equation and said, oh, okay, this equation is constant, this is a constant. So let's call one of them as k, another them over minus k. I solved both of them. X comes out to be this and y comes out to be this. In the last step, all I have to do is just multiply them. So my final solution is this multiplied by this. And that is exactly my option number C. So my option number C is, let's see, a into e की power kx plus b into e की power minus kx, c sine ky plus d cos ky, where a, b, c, d, k are some constants, and we can find this constant using these boundary conditions. But they are not concerned, they are not solving those constants because it is not asked in the question. And I don't think so in 1 minute question they will ever ask you to find these constants. Okay. So more or less our problem is done and option number C is correct. Okay. So that was the way to solve the two dimension, and this is a standard solution for two dimension. So every time this is going to be a solution because I have not introduced boundary conditions. So this is basically a general solution for two dimensions. So for one dimension, what was the solution? For one dimension, the solution was az plus b. For two dimension, the solution is little complicated. It is this. But you have to remember one thing. One side is a function of x and another side is a function of y. That is something you need to keep in mind. Okay. So that is going to be your solution. Any doubt in this one? And yeah, please let me know. So now we should go for a spherical polynomial coordinate. So what if the potential has a radial symmetry? So if the potential has a radial symmetry, basically that means potential only depend upon the value of r. If you change the value of r, the potential will change, otherwise it will not change. So then what kind of solution do we have? Again, I will start with Laplacian equation. Del square v equals to 0. The Laplacian in the spherical coordinate system can be written as this. There are theta and phi part also, but I'm not taking that because your potential only depends upon r. So your Laplacian should actually have three terms: r terms, theta terms, phi terms. For example, curly square v by curly x square, y square, z square. Na? Similarly, in spherical coordinate system also, you should have three parts: r, theta, phi. But there is no point of taking theta and phi because your potential only depends upon r. So I'm just taking the first part of my Laplacian, which is 1 by r square, curly by curly r square curly v by curly r. So this you should remember actually. In JAM also they have been asking this. So this is a very fundamental, very, very basic. In BARC OCS exam they are asking this, right? So 1 by r square curly by curly r square curly v by curly r should be equals to 0. So this is a Laplacian in the spherical coordinate system. This is equals to 0. If this is equals to 0, it means this thing is equals to 0. And if this thing is equals to 0, it means the derivative of something is 0. So basically what you're saying is the derivative of this thing is 0. It means this thing is constant because the derivatives of constant is 0. So this thing is constant. So if this thing is constant, then I can say r square curly v by curly r is some constant. Let's call that constant as a. Okay? So then I just keep my dv on one side and I can bring my r terms on other side. So this is what I will get: a by r square into dr. And in the last step, I just have to do is integration. So if I integrate, my vr will become minus a by r plus b because it's an indefinite integration. So I have to add some constants. So this is my potential. So in case of spherical polar coordinate system, what is the general solution? Minus a by r plus b. This is going to be your final solution. So your final solutions will look something like this. Okay? And that is all. and A and B you can find using the boundary conditions. Once you know the boundary conditions, you can put it inside them, and then you can find A and B. That's all, nothing else. And if you see the question coming in the prelims, they're not asking you anything. They're just asking you the direct formula. So they're saying that the general solution for the radial potential obtained by solving the corresponding Laplace equation in spherical polar coordinate is what? So obviously it is option number C, because in option number C, you see alpha plus beta by R. Yes, it is similar to what we have got, A plus B by R, or A by R plus B. So a very similar form of what we got. A and B are replaced by alpha and beta. Right? So option number C is correct. Direct formula they are asking. They're not even asking you to solve anything, but they are just asking you, okay, give me the answer for this. So we started with Laplacian equation. We make it equal to 0. We only took the R part. We make it equal to 0. Then we say, okay, if this is 0, this thing should be constant. So we make it equals to constant. We got the differential equation. We separated the variables, potential on one side, R on the other side. We did the integration. Once we do the integration, we got our general solution. So this is my general solution. For any radial symmetric, I will get the same solution. Yes, I can put boundary conditions and I can get different values or different results. But in this case, they're not asking you to put any boundary conditions. They're asking you the general formula. So again, but in the IIT JAM questions, you might see some questions in which you have to put the boundary condition. You can easily put the boundary conditions and get the solutions. Okay. So yeah, that this is a main equation you need to keep in mind. Okay. There is one future possible question. This question has not been asked yet, but it could be easily asked. What if your potential is cylindrically symmetric? Right. So that also you need to keep in mind. So in UPSC, they have not asked this question, but in other exam, this is there. So more or less, UPSC can also ask this. There is nothing very difficult in this one. So potential with cylindrical symmetry, then again, we will begin with the same thing. What is del square V in cylindrical coordinates? So it is 1 by S. S is a distance from the axis. Right? How far you are from the axis? 1 by S, curly by curly S of S into curly V by curly S should be equal to 0. Since this is 0, this thing will be constant because the derivative of constant is 0. So if this is constant, so let's call it as A. And then again, separate the variable. So on this side, you will have dV. On this side, you will have A by S into ds. Now what you have to do is integrate. So if you integrate, this will become V. And this will become A log x plus B. A log x plus B. Because the integration of 1 by S is log x. And then B is coming because you have an indefinite integral. So if someone say what is the general solution in cylindrical coordinate, then you say A log x plus B. That is your general solution in cylindrical coordinates. And if someone asks what is the general solution in radial, then you say minus A by R plus B. If someone say what is a Cartesian coordinate one dimension, then you say A Z plus B. And in Cartesian coordinate in 2 dimension, then you say A e to the power kx plus B e to the power minus kx multiply by C sine ky plus D cos ky. That's all, nothing else. Okay. So that is going to be your 4 cases which we discussed. And now I have already uploaded an assignment in which I have PYQs of UPSC prelims questions from Laplace equation. Now only 2 and 3 questions are left which I haven't discussed. They are straightforward questions. Based on whatever you have learned today, you can try to solve them out. And I will try to upload one assignment on this, especially which will include the questions from other exams like GATE or JAM examination. Okay, that you can practice for your better practice. Okay, so that is all for this lecture. I will see you all in the next one. Any doubt if you have, please let me know.